Welcome to the next lesson in our study of reinforced concrete design. In the last couple of videos, we've been dealing with investigating some of the basic flexural assumptions and some of the properties of the materials that make up reinforced concrete, namely the concrete and the reinforcing steel. In this video, we're going to focus now on actually doing some calculations. Okay, and so there are a lot of different phases of life that a concrete member will go through. We have what we call the elastic flexural stress, which is everything that occurs up until a cracking point, and then we have an ultimate stress, which is what we typically use for our strength design calculations and in structural design. So this one's going to focus mainly on that pre-cracking state. So we'll kind of walk you through some of the assumptions. I'm going to show you how to draw the stress and strain diagrams and show you how simple it is to be able to set these equations up if you know what the strain and the stress diagrams look like. It's very, very easy. And then I'll show you a couple of tabular values that we can use in our class. And these are basically calculations of equations that I'll show you, and we'll explain that as we go through. So without further ado, here we go. All right, so what we have here is we're going to start our study of flexural stress by considering what we call a singly reinforced rectangular section, all right? And we're going to abbreviate that as SRR. And what that means is that it's a cross-section, a rectangular cross-section, in our case having a B width, okay, a D height from the top of the beam to the location of the steel, and an H overall total height on this, okay? And that all of the steel is located on one side. It's located usually in the tensile face, or in the tensile region, not necessarily the face, but the tensile region, and it is only there. We don't have any steel that's occurring up in compression. Now, how do you know what's in tension and what's in compression? It's hard to do without drawing the strain diagrams, but I'll show you how we can determine that here in just a second. Okay, for the example that we're going to kind of look at, we're going to kind of consider a beam that is simply supported. It has a point load in the middle, has a span of L, so the distance to the load is L over 2 from each support. Okay, and we know from our basic structural analysis and statics that the moment diagram would then be triangular, okay, with a maximum value of PL over 4 here. Okay, we also know the relationship for mechanics that stress is directly related to strain by Young's modulus. This is our one-dimensional Hooke's law relationship, and so we'll kind of expand on this idea so that if we know what the strain distribution in the entire cross-section looks like, I should know what the stress distribution also looks like. And from that, then we can find forces, because stresses are related to forces directly. Okay, in our labeling system, just to kind of get some of the labels out for us, we're going to say that AS is the area of the singly reinforced rectangular section steel, or in this case, the tensile steel, and that will be our nomenclature going forward through all of the videos. When we get to compressive steel, we'll call it something else, and I'll explain that when we do it. So, but for now, that's what we're going to use in this particular video. All right, so here's what's going to happen. So for any given section subject to flexure, okay, you can recall that we said that stress is equal to a minus my over I formula. That's our equation for stress. And if we know that Hooke's law, as we declared up here, is the linear relationship between stress and strain, then if I can calculate this as a function of y, then I should be able to calculate the strain as a function of y. And that's the basics of what we do. So we know that that stress produces a triangular distribution of stress, with the largest values being up at the top. So I've drawn a couple of pictures here, and I generally draw the strain first, but because I have this formula, let's just jump to the middle one. Okay, and this is our stress diagram. That we have a stress at the bottom that we'll call sigma b. We have a stress at the top that we call sigma t. For a simply supported case, this is a compressive stress, this is a tensile stress, and which is why I have minus and plus drawn here. Okay, but that's the overall characteristic of this beam. Okay, so if that's the shape of the stress block or the stress diagram, then by relationship of Hooke's law, I should be able to say that this is my stress or my strain diagram corresponding, and it is in fact the exact same shape. Now there are a couple of values that we want to look at. Again, we're worried about the strain at the top, okay, which we're going to say is equal to epsilon c, and usually that's taken as 0.003 inches per inch. Okay, and then we have a strain at the bottom, but more importantly than the strain at the bottom, because this whole region is tension, and if you remember, one of the assumptions we made in the last video was that tension in concrete is always omitted. So anything that is a tensile stress, we're not going to count. Okay, instead we're going to count on the steel to pick up all of the tensile work. So the strain that matters to me is not so much the maximum strain in tension, but rather the strain that occurs at the location of the tensile steel. And so if I know that this is linear, then I should be able to set up proportions to be able to refine this strain if I know the distance to the neutral axis and I know the concrete compressive strain at the top. And again, we're going to usually assume that that's 0.003. Not always, but most of the time. Okay, and so that will get us for that. Okay, so these are our scenarios. Okay, now if we look at this cross-section, what we have drawn is a two-dimensional picture. Okay, but in reality, the neutral axis is actually a plane that occurs down the length of the beam at this location in which the strain would be equal to 0 at all locations on that plane. All right, so again, here it's a point, but if I go across the cross-section, then it's actually 0. It'll be 0 here, and it'll be 0 here, and it'll be 0 here, and so forth and so on. So what this is that this is actually kind of, if you think about it, that this diagram occurs at all vertical locations on this beam. So I have the diagram here, and then I have it in the middle, and I have it at the end, and every situation in between. But because we have a constant width, we draw it two-dimensionally like that. So that takes a little bit of kind of getting your head wrapped around why it is that we do that. Okay, now for simple bending, this plane is usually horizontal, at least for horizontal beams, but it's not necessarily the case if I get into what we call a biaxial bending case, in which I have, not only a moment about what would be my x-axis. If you look, this is about the x-axis, where the x-axis is the guy coming this way along the cross-section. Okay, but if I also get it bending in a different direction, then what I'm about to show you may or may not actually be true. Okay, so we're looking at singly reinforced, single direction bending, okay, as opposed to our biaxial bending case. All right. Okay, so actually, I need to show you one more thing. Okay, so here's my strain diagram, here's my stress diagram, and if I know my stress diagram and I know that it has a constant width of B, then I should be able to then turn this stress into a force. Okay, because we know that in general, sigma was equal to force over area. So if I can find the area, or in this case, the volume of that pressure diagram, then I should be able to turn that into a force by just simply rearranging then and saying that F is equal to sigma times A. And that will be the basis of what we're doing. So all I'm going to do is I'm going to take all of this stress that's the compressive block in this triangular portion of the stress block, and I'm going to call that as my C res. Okay, and we know that that's going to be, if I call this distance as x, then the location of where that is acting has to be x over 3. It's the centroid of the triangle. Okay, and then the T res we know is occurring at a distance of d down from the top, and we'll show how we locate that here as we go forward. So that's kind of our approach, and this is the approach for all of concrete analysis. I draw a strain diagram, I get the stresses, and I turn around and figure out what the forces are doing. That's it. If you can lock your head around the procedure to do that, you're practically home free. We've about got this thing licked. Okay, now again, there are some tricks, and there's a little bit more to it than that, but just, you can do it. Keep after it. All right, so here's what we're going to do. So let's take that last picture that we had. Okay, and so if I'm looking at computing the tensile and compression resultant forces, again, we said we're going to take force equals stress times area. And so this becomes my diagram. So here's my neutral axis again. Here was the compressive triangle that we showed on the last one in my C res. Okay, and it's located at some location. Okay, and then the T res is the force in the tensile zone. Again, we've neglected everything in tension in the concrete. Okay, so this is all the forces that are happening. And so together, C res and T res will form a couple. Okay, and that will become the internal moment capacity of this. Now let's go through some labeling, and we'll show you how they handle with the elastic flexural stress calculations. They're going to find the distance from the top of the beam to the neutral axis as being some distance of kd. Okay, and remember, d was the depth from the top to the steel, so k is kind of a fraction. It's a percentage of the depth that goes from here to here. Okay. The distance between the compressive resultant and the tensile resultant we call as JD, right? And again, we don't really know this value, nor do I really care at this point what it is. We can find it, okay? But for now, we're just going to set up our labeling system this way. And then D is from the top of the beam to the centroid of the steel, right? So when we had just a single bar of steel happening here, it was to the location of the bar. But if I get into multiple bars or multiple rows of steel, then it's actually to the centroid of that pattern, if we start to kind of look at it. So that's why in the singularly reinforced, we typically just draw it as all as a lumped area of steel at the centroid of the pattern. We'll show you some more about that as we move along. All right, so what we know from simply supported is that compression is in the top, tension is in the bottom, okay, and that this line across here is the centroid of the steel. So if we take advantage of that, then all we have to do is go in and figure out, well, how do I calculate these resultant forces? So if we call sigma top, and we're going to label that because what we're after is that's the critical stress in the concrete. That's where it will fail first. Because as I increase the load, this point gets bigger. Okay, and so this guy will reach his limit first. Okay, and so we're going to say that sigma T is this FC value, the stress in the concrete at that location. All right. So for rectangular sections then, we know relative to that picture, we can compute things then as being basically this piece as being the area of the triangle, okay, and then multiplied by the width B, which is going into the board, right? Because again, what's kind of happening here is I'm taking my cross section, okay, and I'm getting these big blocks looking something like that, and here's my AS. All right, so this is actually kind of a, if you look at it, it's kind of a prism of stress that's happening there. So all I have to do is just find the volume of that prism. And I can do that fairly simply, that it's 1/2 the stress at the top, sigma T, multiplied by that KD dimension, which is the height of the stress block, okay, multiplied by B, the width, which was this guy there. Okay, and with that, I have now taken that pressure, found the equivalent volume of that pressure block, and that is C res. Okay, and that will get me that value. All right. Okay, and so you'll see it. Now, again, some books will rewrite it a little bit differently in terms of FC. That's why I show it in both, in terms of sigma T and F of C. You can rewrite the exact same equation that way. Okay, so that's that piece. The tensile resultant then is simply the area of the steel, which was this guy, AS, multiplied by whatever his stress is. Now, typically we want that to yield because we want the steel to fail first because it produces a more ductile failure rather than sudden crushing of concrete. So there will be some ductility checks that we have to do and some strain checks that will start to affect our calculations. But ultimately, this is F of S. And usually what we want is that guy to be ASFY. Okay, if we're in a truly ductile state, that will be true. But again, sometimes it is, sometimes it isn't. We don't know until we do the actual stress calculations. All right. Okay. So from equilibrium then of my diagram, if I sum forces in to the right direction, sum of forces X equals 0 on that block that we just drew, I know that I have a minus C res because it was acting to the left, plus a T res to the right, and all that has to be equal to 0. Right? And so if I do that, then I can set up a relationship, and look at what happens. I get a half FCB times KD plus ASFS. Now again, that first term is negative there. But now all of a sudden I have a relationship that exists between FC and FS. Okay, and it's a function of KD. So if I can find one, I can find the other. So if we assume that this is going to yield, then I can find the corresponding stress that occurs in the concrete, and I can check it against its corresponding limit. So all I've done is I've basically taken that equation and done a little bit of rearrangement of that. So ASFS is equal to 1/2 the stress in the concrete B times that KD distance. That's how we handle our elastic flexural stresses here. Okay, all right, now going back and again looking at our picture, all we're going to do now is we're going to sum the moments on this. Okay, and when I do that, then we're going to sum moments around the residual, because this whole thing, this whole section is being subjected to some internal moment, which we're going to affectionately call as like an MN, like a nominal moment associated with that. Okay, so if I do that, and I write my equations on this, what we're going to do is we're going to sum moments about the compressive resultant, because it's the most complex of the two of them. Okay, and so I can calculate the moment on the section to balance ASFS, this is T-res, multiplied by that moment arm JD. And we'll set all that equal to 0. Okay, and so if I do that, we know this quantity, ASFS, that if I could do the same calculation about the tensile resultant, it's still the same internal moment, but now I can do 1/2 FCB KD JD. All right. But the reason that I don't do that is that here J and K were unknowns. All right. They're kind of based on the reinforcement ratio in the strain diagram. Here I get 2 of them. There I only get 1 of them. So the top equation is actually a whole lot simpler to kind of deal with. Okay. But we want to be able to kind of correlate these factors to each other. So all I'm going to do is I'm going to rearrange things a little bit. Okay. And so since I know that this is the moment equation and this is the moment equation, then if I rearrange this, then it stands to reason that this term, the second term, should be the same as the second term in this guy because, again, both of those are equal to 0. All right, and so if I do that, I get ASFS times JD is going to be equal to 1/2 FC times B times KD times JD. Okay, and then all we do to find the ratio of the stresses is divide one by the other. So in this case, I'm going to take everything on this side and divide it through on the other side. Or in this case, I'm going to bring FC over and then take everything else to the other side, and I get an equation that looks something like this. And notice that the JDs will cancel out. Okay, and so what we see is we see that K times BD over 2AS is equal to the ratio of the stress in the steel to the stress in the concrete. And that's pretty cool, because all that says is it says that if I know my area of steel and I can find K, then I know the ratio of those stresses. And with that, we can start to actually do some cracking limits, because when it gets to cracking, all I do is I set a value on FC, or if I know that I'm yielding, I set a value on FY. Okay. All right. Now, the one piece that's kind of new to us on this is looking back at our strain diagram. So let me go pull that page here a little bit. Okay. And so if we go through and we look at this, okay, a lot of what we do comes into how do I find these strains? Okay. And so we're going to take our epsilon CU, which is this top value. We just defined this guy as KD, right? That it was the distance from the top to the neutral axis, and the neutral axis is the same at both the stress and the strain block. Okay, and then if we do that, then this distance right here has to be D minus KD, right? Because it was D from here all the way down. So, and again, if I can find K, I know everything. K is what defines the strain diagram on that, and so we should be able to then move into setting up the stresses in our steel, and that's all we're going to do. Okay, so we're going to use our strain diagram to set up this relationship. Okay, that the proportion of epsilon S to epsilon C, if we look back, and I'll kind of set this on the side, and then we can do both at the same time, that epsilon S goes to D minus KD is the same as epsilon C going to KD. And so that's what we're saying. So here's the epsilon S, there's the D minus KD, it's the same as epsilon C going to KD. And again, we can do that because this is a linear function. All we're doing is just solving for proportions. All right, so what we do is we say that the strain in the steel as a corresponding to the strain in the concrete is then 1 minus K divided by K. Okay, that K parameter is the factor that defines our strain diagram. All right, now recall from our transform sections in the last video that the ratio of Young's modulus in steel to the Young's modulus in concrete was our N value. Okay, and generally speaking, N is usually somewhere between 5 and 11, depending on your strength of concrete for normal applications. Okay, we can then go in and start to set up our stresses. We know that Fs is equal to Es times epsilon S, and we know that Fc is Ec times epsilon C, regardless of how you calculate them. All right, and so we had this equation that we set up from our strain diagram that was epsilon S times Ec gets me to stress on this. And then if we recognize this term, that's just N. Okay, and so I can say that the ratio of stresses then is N times 1 minus K over K. Okay, super easy. Let's look at that. Okay, and here's the part where it gets really wild. Okay, if I recall from that first relationship that we had related stress in steel to stress in concrete as KBD over 2 times the area of steel from that second step, now all of a sudden we can start to kind of relate that to this new equation that we have. Now, I'm going to sidestep here for just a moment and come up with what we call, it's a common parameter known as the reinforcement ratio. And what it is it's basically the area of steel, okay, over the gross area of concrete. Okay, and again, that's the area of the tensile steel. So this is the tensile reinforcement ratio. okay, is what we do. And for years in older versions of ACI, this was a major design parameter, and we had a lot of checks that we had to do. Now in the newer format, with starting with 318, the 2014 edition or the more current 2019 edition, they do things a little differently. But to this day, I still do some things with this guy just to kind of as a check to get me started on the design process. And like I say, I'll show you some of those tricks a little bit later. Okay, but what happens as I start to set all of this is that if I recognize this as a constant, because this doesn't change, you specify your steel and you have your dimensions, you know this. All right, and so if I know that that's the case, if you look back up in this top equation, he's hiding right here, right? See AS and BD, so if I can say rewrite this as K over 2 rho. Okay, and so that becomes FS over FC is now K over 2 rho, that ratio. So all I'm going to do now is I'm going to set all of this equal those two FS over FC equations. I got my K over 2 rho equation that we just talked about, and then I've got the equation that we had here for FS over FC, which is 1 minus K over K times N, and they're the same function. So I can come in and say, all right, K over 2 rho is equal to N times 1 minus K over K, and all of a sudden, what pops out is I have a function in terms of K, and this guy is quadratic if you rearrange it, right? But I can come in and say that we have, K squared equals 2 rho N times 1 minus K. That's a quadratic equation if I rearrange it. And so if I apply the quadratic equation to this, I can solve for K. Okay, and that K to solve this equation will be this kind of ugly function, the square root of 2 rho N plus rho N squared, all under the square root sign, minus rho times N. But look at what we just did. I took a whole bunch of unknowns coming out of an elastic flexural stress block, and I turned it into an equation with a constant, a rho, which is a constant, an N, which is a constant, and nothing else. I can calculate K for any reinforcement ratio or any amount of steel for any section BD. That's powerful, right? And that is just awesome. So now we can locate, and if I know K, then I know where the neutral axis is, and if I know where the neutral axis is, then I can find everything else, right? So it's easy enough to plug in this into your calculator and calculate K directly. In the old days, dating myself here a little bit, we would tabularize a lot of this stuff, and so it's not uncommon to see this in some of the more popular design manuals or design books. Okay, but all they've done is basically related K and J to each other, because it turns out that J is related to K as well. Okay, but for any given N value, 7, 8, 9, or 10 on this, and for any row, I can read off what the K value is. And all that is just simply plugging into this formula that we just derived. Okay, and recognize that J is equal to 1 minus 1/3 of K, and that comes out of those relationships on the strain diagram as well, or on the stress diagram, sorry. Okay, and so if that's the case, then for any K value, I get my corresponding J, and then for any row, I get the corresponding K. So once I input a row, I know K and J. Basically, I've defined the stress strain diagram for the elastic state, and that's pretty wild. All right, so let's go back in, and we'll kind of show you where that J equation actually came from. Okay, so we go back to our resultant. It's KD from top to bottom. It's C res for the resultant. We know that this location from here to here, we said is 1/3 of KD. And then we define JD as being basically this moment arm that exists inside of here. Okay, and so that's my JD. And so if we go through and we kind of look at this, we can actually show then that since D, the depth D is 1/3 of KD plus JD, I can do a little bit of clever rearranging on this thing, and you see that D is common to every term on this thing. Then I can solve for J as being 1 minus K over 3. That's where that formula comes from. It's all coming off of these stress strain diagrams. So if you can understand the stress strain diagrams, then man, you are in business when it comes to elastic flexural stress analysis. All right, so once I do that, then I can go back to my equations that had the moments. And so if I know my applied moment at the section that I'm looking at, and I know my area of steel, I now have JD, I can find the stress in the steel. And correspondingly, I can find the stress in the concrete using the other equation. Okay, and we're good to go. All right, so now for SRR, all we have to do is put in a couple of limits on this. That if my FC value is less than 7.5 root F prime C, if you recognize this, that's good, because that was our modulus of rupture. That was our tensile limit state for a flexural beam, right? Remember, we come in and done, for a beam and said that if I do this test on it and push down, that I will get a flexural crack. And in an unreinforced beam, this is the modulus of rigidity for that value. This FR, that's 7.5 root F prime C for that scenario. That was one of those three cases I showed you back in the material properties. Remember, we talked about uniaxial tension, flexural tension, and then split cylinder. This is that flexural tension case. Okay, so if I do this, I now know that my section is uncracked if I'm less than that limit. Okay, and similarly, if I find out that Fs is greater than Fy, okay, then we know that the steel is yielded. Okay, but now, one thing to admit, in an uncracked concrete section, usually the stress in the steel is typically much less than Fy. Okay, but once we get into our ultimate calculation, our ultimate strength, this guy will start climbing really fast, and it will become a measure of our ductility, and it's something that we actually want to have happen. Okay, now, some of the assumptions that we got to remember in this is that this method that I've showed you basically assumes that both steel and concrete, both are still elastic, but then again, how do we really know if this is the case? Okay, and that's kind of the question that will lead us into our next video. So again, kind of like what I did the last time, I'm going to show you kind of one of the worksheets that I would work for this, that if I gave you an applied moment and that transformation coefficient N on this, you should be able to find me the elastic stresses in concrete, okay, and the corresponding stress in the steel. And so I kind of walk you through the procedure, and you use the equations that I just showed you. And again, for my students, in my class, this is one of the sheets that you guys work as kind of a class activity. For my other viewers, you guys can work through this and you'll get it. It's not that hard. Okay, so all I've done is I've taken a rectangular section. I have a width of 13 inches. I have a depth of 31.5 inches. The total height is 34, and I'm putting 3 number 9 bars in here. All right, so all you got to do is go look up what's the area of steel associated with 3 number 9 bars. Write it down. What's the reinforcing ratio? Again, that was AS over BD. Here's my B, here's my D. Now notice it's not B times H, it's B times D, because again, we kind of neglect the strength of the concrete even beyond the bars as well, because that'll be the first stuff that cracks. And then once I have rho, I can get K, and once I have rho, I can get J, and once I have K and J, then I can calculate the stresses. It's really, really simple and really, really straightforward. Okay? So with that, we will call it a day. Now, again, as always, if you will leave us some comments or leave us some feedback on this, if you've got any questions, I'll be happy to answer them. Otherwise, like and subscribe, like the video, subscribe to the channel, and we'll see you all next time. Thanks. Have a great evening. Happy engineering. Bye.